Dr. Vikram is principal engineer from Intel, and he's right now focusing on the deep learning performance as an AI performance architect. He has more than 25 years of experience and has delivered optimized software for a lot of challenge and also before he joined Intel, he holds the faculty tenure track faculty at Oregon State University. So welcome, Vikram. So please go ahead with
Okay.
speak. Okay.
All right. Thank you. Yes, this is Vikram Saletore. I'm from Intel. And can you, firstly, thanks for inviting me to the workshop. And I just want to check, can you see my slides?
Yes, we can.
And can you?
Yeah, can you turn on the presentation mode?
Yes, I can. And also, if I just want to check whether the slides flip through.
Yes.
Do the slides flip?
Yes.
Okay, good.
It works. Thank you.
Okay, great. Yes, so as let me just, okay. So yeah, I'm in part of the Intel architecture and graphics software, and my focus area has been for the past, at least for the past, more recently, has been on hardware aware and auto ML performance. I'm more interested in the performance aspect, and I'm now getting more into auto ML kind of work and also hardware aware. And I also work with customers, and there are a lot of benchmarks, and you'll see that. But I'm going to point out some use cases that actually have worked with some of the collaborations that we've done with Surfsara in Amsterdam, and also CERN Open Labs in Geneva. So let's get started. And this is sort of in the realm of AI and HPC convergence. So one is, as you know, for training, we use existing HPC infrastructures to create new models. And I'm going to have two use cases that I'm going to describe, one both with Surfsara, one on histopathology and one in retrosynthesis. And in the second part, I'm going to talk about how AI is actually trying to displace or replace modeling and simulation with AI models. Actually has great benefits in both cases, because in this context, the amount of energy or power required to actually do post-processing of whether stored data or generating data is highly compute intensive, and how AI model can, once trained, can actually use inference too. And so one is the one with CERN Open Labs, and the second one is with Surfsara on Deep Galaxy in astrophysics. So let me start with the first one, histopathology. So as you know, histopathology, this has whole slide images, and this is in digital pathology. And these slides are huge, 200 pixels by 200 pixels. And you would like to do semantic segmentation and classification. So Radboud Medical University in Netherlands actually have data sets, and they have challenges called Chameleon 16 and 17, and they're with high clinical relevance. As you know, there are a large number of women who get diagnosed with some kind of cancer metastasis, and the survival rate, in 5 years is less than 15%. So early detection, semantic segmentation actually can help, and classification can help. So these images are actually the whole slide images. These large images are at the different magnifications from 1x all the way to 40x, and they're data sets that are publicly available. So for example, 16, just as an example, this is like a metastatic region. You can see what the radiologist actually has indicated. And if you go from low res to high res, mid-res to high resolution, you can actually see that one on the left side of the is the white, here this is normal, the other side is actually has metastasized. So the final the higher resolution actually gives you a lot more information in context of the contextual information from the low res. So what we have used is the DeepLab V3 from Google's Brain team, and it's improved semantic segmentation by learning some orientation or regions of interest. And in this case, as you know, it uses something called Atris convolution to trade off precision and runtime. And Atris convolution is nothing but, as you know, is dilated convolution with a rate of, in this case, it's a rate of 66 to 24. And the one we use, the DeepLab V3, has been pre-trained on exception 65 on the Pascal VOC. And this is, as you can see, it's an encoder-decoder network. I'm not going to go into the details, but there's a mask that is actually provided, a binary mask, which says, it's a tumor or not a tumor, and that actually helps get to the loss and detect the and do the segmentation at pixel level. So what's, I guess, a lot of the talks earlier have been talking about accuracy. And as you can see, the accuracy really depends on the patch size. The patch starts with a P, patch, not a batch size, but patch size. That is size of the patch, which could be 256 by 256 all the way to, let's say, in this case, what I'm showing is 2048. And you have different MIOU you can actually get to. It also depends on the zoom levels of this data set, and whether it's, whether you're using a 256 at zoom level, or, pixels, or the patch has been carried, 512 in this case. And the larger the higher the zoom level, you can actually get higher accuracy. But the cost is this. The cost is that you require increased memory, and that's the trade-off. Is, as you can see, most the HBMs have 32 gigabyte, and now they've increased in capacities, but what you see is that it increases with pixel size, and the required memory increases. And I think that's been pointed out in many of the talks earlier. So we have actually scaled this out to a large number of nodes on Intel's cluster, on Xeon, and with a patch size. And this, what I show, is a patch size for 512 and zoom level 4 all the way to 256 nodes. And with a, of course, with 80% scaling efficiency, dropping at 256 nodes. Training performance we also looked at the 2K by 2K pixels. We had about 600 images, and it's not on a large cluster, but on a 6-node cluster, it took about 17 hours to train all the way. And as you can see, the MIOU actually improved with large. So it does. So accuracy, you can get accuracy higher with larger images. Most of the hyperparameters tuned in our work we have been using Optuna, which is an open source Bayesian optimization with some kind of early stopping and or TPE in this case, and so we've been using Optuna for that. So the conclusion is that the accuracy is a function of patch size, zoom level, and memory usage, and that's where the trade-off comes in. So the question is how it depends on the customer, how accurate they want it to be, and what they are willing to live with. But that's the trade-off, for in this case. I'll take the second one, which is a sort of a unique case, but it's some work has already been done earlier. And this is with Surf-Sara on retrosynthesis. So what is retrosynthesis for organic chemical compounds? So retrosynthesis is predicting a smaller molecules that can be used for synthesize a target molecule of interest. So for example, it's a sort of a chemical reaction. There are source molecules, target molecules, and there's some kind of translation going on. So what earlier research has been done is actually looked at as attention models. and or the language translation model in this case, and it's treated, and there's a SMILES representation of these molecules, and there's a 50,000 data set available from US Patent Office on these. So as you can see, this is a chemical compound and its source compounds, and the prediction is what source with the higher accuracy that what can be predicted. So using a attention model, I'm not going to go too much detail into the attention model. I guess you guys all know. Essentially, it's a in a sense, it's a, for example, English to German translation. It's about large. It has 6 encoders, 6 decoders, and large number of attention heads. So what we did, we took the attention model and sort of reduced it to 3 encoders, 3 decoders, and reduced the number of attention heads, and then also reduce. Of course, it reduces the size of the weights, 5.1 million, and so we use that to train this model on the US Patent Office data set. And so this was using PyTorch, and we built on the earlier work that was done in previous research. We had some challenges of getting to convergence, but we had to use ensemble techniques to actually find the best learning rate using Adam optimizer. It did train, extremely well onto large number of nodes on Xeon cluster, on an HPC cluster. So this is again another use case that actually is being used on an HPC cluster. And here are the results on some of that. I mean, given that it's a small model, it scales well. On 128 nodes of cluster, it can actually complete in about 3 hours. Oh, sorry, 3 hours, 3.5 hours, and on 64 nodes, it can complete about in 6.5 hours. With a let's say if we use a beam search decoding strategy, then we can actually improve the on the base over the state of the art accuracy from the early work that was done, and we reached this score, as you know, very similar to what the blue score has for the bilingual for the language translation. This also has a score of 43.6%. That's so what I showed you was 2 use cases that actually use HPC infrastructure. Now I'm going to talk about how some use cases that actually would try to displace or replace some of the HPC modeling and simulation. So this is the first one is with Open Labs. It's in the high energy physics use case. Those of you who attended the morning session from, I guess her name was Tia and Claudio Donor from Palo Alto Networks and CERN. Actually, she gave a very good overview of the Large Hadron Collider and the particle. But very similarly, I mean, this Open CERN, the CERN Open Labs is also in CERN in Geneva, and they use actually Monte Carlo simulations today, and primarily. And as you can see, the Monte Carlo simulation or Monte Carlo related simulation takes a huge chunk of compute today at CERN, almost like 40%. And what CERN is saying is that when they get to 2028, they would need a compute requirement by 100x what they have today, and that you can imagine what's the. I mean, CERN does have large clusters of systems that actually they use around their machine Monte Carlo simulations. So one of the is, can AI help, and can AI help because the motivation here is if they have a trained model that actually can produce particles, which are essentially doing by simulations, if they can produce the same particles with the same accuracy, then the inference is the motivation. So I'll get to that point. So we worked with CERN, and they developed a model, in a sense, the number of events we actually had was to work with was about 200,000. It was a three-dimensional 25 by 25 by 25 image where energy deposits of the electrons or particles that are coming are deposited, and that actually gives you some kind of a reading on the on those showers, particle showers. So so the architecture was resulted in a 3D GANs. GANs, as you know from Ian Goodfellow's work on GAN or generative adversarial networks. Essentially, it trains two networks, generator and discriminator, random input going into the generator. Discriminator has the real images going, or real, in this case, real the particle shower or come from simulated, and until the discriminator discriminates against the output from the generator and trains it, so that they actually match. I can't tell the difference between the fake and the real. So we actually were, and this is our work from last year. And the reason I'm presenting this is because I want to show you how we get to actually the inference part of it. So this was done last year. We showed that, that we actually can train it on 256 nodes to, essentially very good scaling. In addition, the real interest is how accurate, and this is not accuracy, what the loss or accuracy, or there's for example, it's not like mean square error or something, but it's for CERN, it's important that in their case, post-processing of that accuracy actually is important, and that is this the graph on the bottom right that you see it's a ratio of ecal over EP over electron volts of energy, and how close it is, and in the middle is actually what they are interested in, and this seemed quite acceptable to them, this kind of accuracy. So even at one node, or as you can see, one node is much better, 256 node differs, but it was acceptable too. So the question of accuracy is how willing they are to actually tolerate this accuracy. So so the motivation, as I said, was inference. The inference today, or I shouldn't say today, but in 2018 or 2019, on an older generation, it took about 1700 milliseconds per shower. Okay, and running these inference to generate data actually today takes 0.85 milliseconds, or that is 850 microseconds. So you can see the speed up is like about 20,000x. So the question is, given that we have this kind of way to generate data, they think about the amount of energy or the time spent in just running simulations with Monte Carlo. So the question is, how can we further improve this performance via quantization? So let me go to quantization part of it. So the 3D GANs actually requires a 3D convolution, quantized. As you know, so this work is sort of a work in progress for our 1DNN from Intel. We didn't have it ready at that time, so we actually developed a new model, in a sense very similar to the other model. It's which actually takes the two-dimensional convolution layers to reproduce a 3D volume. So it still takes the same data set, same image, but the model is now a two-dimensional, but does a three-dimensional convolution and does a two-dimensional convolution, but actually generates a 3D volume. And so we actually train that model, and we want to quantize it. So Intel has recently open sourced a tool. It's called Intel Low Precision tool. It's an auto quantization tool. In a sense, it's used actually to deploy low precision inference to deep learning frameworks, and it supports TensorFlow, PyTorch, MXNet. It's also available through Intel AI Analytics Toolkit, and it has been used for. If you go to the site, and this is a link actually. If you go to the site, it has almost like 30 to 50 benchmark models have already been quantized. I'm going to give you a flavor of that. But what it does have is it has a framework adaptation layers, as you can see, and then on the top it has the quantizer, it has a pruner, and it has extensible tuning strategy. Now, what does that mean? the tuning, because it's an auto quantization tool, it also has user-facing API. So one can actually use, for example, Bayesian optimization, hyperband, or tree parson estimators, or reinforced learning, and that can be also be used. So what's the workflow for this auto quantization? As I think it was Raghu from Facebook who indicated, that I think he said that there's need for this auto quantization tool, and yes, that's exactly what it does. You basically have to import into this in your Python program, and then actually you can, it'll quantize, the tool will quantize the model for you. So the way it would work is that you takes an FP32 PB graph, for example, it will quantize it to a low precision model. It also prune it. It can and generate a sparse model. It'll evaluate the metric. It'll look at the tuning strategy, whatever that user is defined or whatever user has selected. And if it doesn't meet the accuracy, it goes to the next cycle. So it's a automated tool. One doesn't have to spend manual any effort. Essentially has to restart it, and a lot of the models have been quantized overnight, running on a single machine. So what are the so what do we see? This is just some selected ML benchmarks. As you can see, I think Raghu was saying at least 2x, but we are actually seeing in the range of 3 to 3x, up to 3.8x within 0.6% drop in accuracy. So we use this tool actually to do our work, and on the CERN's GANs model. And as you can see on the left is the operation times, that how some of the FP32 operations have been either eliminated or reduced, and of course you have the overhead of adding quantized operations with this quantized matmos or quantized Liu-Relu, all these, the ones in the red. And as you can see, what the throughput is, as you can see, is we get about 2x, at least on this one. The reason for we get a smaller throughput with GANs compared to benchmarks is because the total number of operations that actually are quantized is about, or what could be quantized is in this GANs model is about 60%. And Amdahl's law will tell you that you're not going to see a large percentage increase. So the question is, just having that quantized graph and generating, so let's say, have some convergence meeting the accuracy, is not enough for actually a use case. The use case is, for CERN, for example, is to look at the physics accuracy, because that's what is important to them. And it's because this has to be done post-processing. So once it's quantized, we look at the physics accuracy and see how these shower shapes are in the X, Y, and Z directions. And that's the MEC values are based on different models, and as you can see, the lower the difference between is what actually gives us So we have also used the Intel low precision toolkit, gives the best. We have also looked at TF Lite. We also looked at TF Lite Int 8 and 16. They don't do as well, and our tool actually does fairly well. Plus, it's automated. So where does that leave us? I talked about the 20,000x, remember? And that was, of course, with TensorFlow. It was last year, TensorFlow 114. And on an older generation, the previous generation architecture, we optimized going to TensorFlow 2.4. We also move to the second generation architecture on Xeon, and we get a bump of almost 2x. That gets us to about 38,000x improvement over the software. Quantizing gets another 1.9x improvement, so we actually get about 68,000x improvement over software. So what does this mean? What this means is that CERN doesn't have to generate data using quanticolor simulation. they can actually now generate on the fly. They don't have to store it. They actually have to generate at this improved inference rate. And that's, in a sense, it's sort of trying to, for this detector, it's actually trying to reduce or eliminate the HPC simulations. So the last one is on Deep Galaxy. Deep Galaxy is to reduce the physical properties of the galaxy mergers, and this is an astrophysics use case. It's led by actually Maxwell Kai at Surfsara, and so this is the typical how the universe, our solar system was formed. Okay, they want to know how for any given star system or galaxy, what are the properties of and how do they merge? How did they merge? How do they actually merge? Because the images that are received from Hubble are in some time, and the galaxy probably don't even exist anymore. But the interesting aspect for astrophysics is how these galaxies merge and form. So I'll show you in a sense, the way it starts is, I mean, this is like initially it was gaseous, and it's just a small simulation, and when then it becomes dense, and I'll speed it up in the interest of time, and galaxies begin to form, and our star systems begin to form, and it explodes, as you can see, I hope you can see the animation through the network. I hope it's not very slow. Anyway, so this is how it's forms. So images, as you know, are received from Hubble and telescope. Hubble has been there for about 30 years now, and after they fixed the glitch and the lens, now I think they're receiving extremely well images. There's also another new telescope called 30-meter telescope, but Hubble telescopes had still very outside the atmosphere, so it's very clear. So the question is, a large number of images are obtained, but the question, and they have to be processed. So sometimes they actually have volunteers to process these images to know what these images are and what they look like, and that's an extremely intensive process, and they have to be stored somewhere as well. So another is an example is these couple of galaxies. So the question for astrophysics is, I mean, this is not for entertainment only. I mean, this is actually astrophysics would like to know what is the morphology of the galaxies, tell us about their histories, and that's what they want to know. So what happens is that from a simulation to observation.
Sorry, Dr. So we have 5 more minutes left.
Okay. Yeah.
Just give you a heads up. Thank you.
So the astrophysical problem becomes a pattern recognition problem. Okay. So as you can see, I'm just going to quickly fast forward this. How it's a simulation of galaxy merger simulations, and to form, they collide and they merge, they form star system. So what we did was we took this. There are a set of images that we took, a small number of images actually, large image sizes, and we used a variable autoencoder. Used because this. So if you take X and generate Y, you have the labels. But now, sometimes we don't have the what if they don't have labels? Then we actually, that's unsupervised learning. So we actually decode it, get an X hat, and then try to minimize the X and X hat. They are flattened, sent to M hat, and then going forward is we go through an encoder and decoder for an VIE that actually generates this M hat prime, and then they can be minimized. The loss can be minimized between M prime and M prime hat. I'm not going to go detail, but the backbone that we used was EfficientNet B4, which has a high much higher, significantly higher accuracy than, for example, ResNet 50. It is same as SCNet, but is about 8x reduction in trainable parameters. So it's so we have used this for the different size pixels, 512 by 512. We were able to train it in like about 12 epochs in about 15 minutes on 256 nodes. And then with larger images of 1K by 1K, we were able to train it in about 60 minutes. We also looked at the scale out performance efficiency on an Intel Xeon cluster. And these are, so the total number of images is about 29,000. And as you can see, it at 512 workers, which is 4 workers per node or 128 nodes, is about 73%. It drops to 52% and at 256 nodes. So what does this mean? So processing these images and running simulation takes about, for these astrophysics, takes about 2 days. And now replacing those simulations with deep learning models takes about less than 2 seconds. So what you see is sort of the impact of this inference, resulting in a speed up of close to 100,000x, 80,000 to 100,000x. And that's what they are looking at. So my last slide is here. Benchmarks are important. Use case do matter. That's where the actual organizations use. For example, this is where in this space of x-axis being the total memory consumed, y-axis being the total input size, input image or text or etc. that's going into the network. So this is the diagram that actually Kushal and I worked when Kushal was at Intel. Now he's at NVIDIA. So benchmarks are in this bottom left. But if you look at where the use cases that we have looked at, I mean, there are other use cases that I'm not talked about. There, for example, Novartis is one, and Deep Galaxy I show here. Dell, I've done some work with Dell systems on radiologists. And then I told you about the histopathology, and then Max Planck Institute. So where these are in this top right. So, and as you can see, of course, GPT-3, 2, and 3 are way out in the, but the the size of the input image going is much smaller. So this is how so you require memory, you require you require memory, you require compute, and that's some of these use cases are. So I'll stop here. This is my last slide, and thank you for inviting me for this. So if they have any questions, I can take it now.
Okay, yeah, that's very impressive talk, Dr. Vikram. So we hope we have more time for you to show the whole simulated video. So that's very interesting. So any question from audience? Okay, so I have a question. So
sure.
I think one thing you talk about is one is we have a good user case, and but the user case requires large amount of data, and then for the computing platform we have limited. So you talk about the quantization. So based on your understanding, like for the 8-bit quantization, do you think it's sufficient for most of the user case, or what's your opinion?
So I think we can go down on the quantization to lower precision, and if it is supported in the architecture, there has been, I think that's what we are looking at. We are trying to see making this hardware aware, quantization and hardware aware training. That makes it how we can actually do that, and that's is work in progress. But and we have seen some early results. We've seen on are extremely well. If you look at Professor San Hong's work at MIT, he graduated from Stanford last year, I think. His work on proxy NAS actually is trying to actually address some of that hardware-aware training. So yes, there is scope for that. I mean, definitely, definitely there is scope. I think we can go down on and still get the same accuracy. And I think it was in the earlier this morning's talk that I think somebody said was, what is important? What is the accuracy important? Everyone wants accuracy, but then if you say it's 10x better or 10x smaller model or 10x faster model, I think those things people have sort of trade off that. But yeah, but there is as long as there's some tolerance is there, I think people are willing to use. Definitely, there's scope for lower precision.
Okay, yeah, thanks for a great talk and answer.